Ideal diode current equation. Important thing is, if you even understood the topic, how crucial is the use of inverted commas, you will see now. Let us assume we place the inverted commas like this. Then the meaning of this will become ideal diode current equation. If this was the actual meaning of our topic, then we would be finding current equation of an ideal diode. But this is not the case. I will later describe all the major characteristics of ideal diode in another lecture, but here it is sufficient to know that one of the characteristics of ideal diode is that it has infinite current. So basically there is no current equation for ideal diode as it is already assumed to be infinite. Our topic is actually ideal diode current equation. Basically, we will be finding current equation of a practical diode, even though it is written just diode, but it is already assumed that the practical diode is taken into reference. Now, the first term in our topic is ideal. So, what does it signify? The term ideal here comes because of another approximation, which is Shockley ideal diode approximation. The next question is obviously, what is Shockley ideal diode approximation? To answer that, first suppose we have PN junction with P-type region, depletion region and N-type region. Shockley diode approximation simply says that the total current which is going from one end of the depletion region is equal to the total current which is coming out of the depletion region. It simply means that there is no recombination taking place in the depletion region. And for our easier analysis, we mark this point 0 and this point also 0. Here we call it xp0 and here we call it xn0. Also, the distance xp, which is a distance from the end of depletion region existing in the p-type, is positive if we move towards left. And opposite can be said to be true for xn, which is a distance from the boundary of the depletion region, is positive if we move from left to right. It is quite strange as in Cartesian system, if we take one side positive, then automatically we take the other side negative. But here we have defined two different parameters. One is xp and the other is xn, which is defined for different directions. Also, depletion approximation is also valid here. Even though we do not use it to derive the equation, but still its postulates are valid here also. Like electric field is 0 outside the depletion region. Similarly, absolute potential is constant. Similarly, all the dopant concentration, either donor or acceptor, all are ionized in depletion region, whereas all are non-ionized outside the depletion region. Maxwell-Boltzmann approximation is also valid here. You should be able to recall by now what is Maxwell-Boltzmann approximation. The concentration profile for forward bias junction will look like this. Red line represents the concentration of holes and the blue line represents the concentration of free electrons. The dashed line is representing the concentration profile if the diode was unbiased. I hope you understood what are different parameters in this diagram. Now there is no need for such a big diagram. There are two possibilities of current. One is due to the drift current, which is caused by the generation of electron-hole pairs near the depletion region, and due to their close proximity to the depletion region, they are driven across the depletion region under the influence of electric field. Another current component is caused due to the diffusion of majority carriers and hence referred as diffusion current. Let's assume that the diffusion current component is I diffusion, whose direction will be from left to right. Similarly, we can also find that the generation current component is from left to right. Also, we know that when the semiconductor is unbiased, then diffusion current is actually equal to generation current. If we take current flowing from left to right to be positive, then we can also write that diffusion current is actually equal to absolute value of generation current. Now, it is observed that when we apply an external voltage, then there is actually no significant effect in the generation current, but diffusion current increases by a factor of exponential Q into V external divided by KT, where V external is the applied external voltage. Therefore, net current will be equal to diffusion current under the influence of external voltage plus generation current under the influence of external voltage. I net will be equal to I diffusion into exponential Q into V external divided by KT, plus we can simply replace the value of generation current under the influence of external field to be equal to unbiased generation current. If we assume that diffusion current for the unbiased PN junction is equal to I naught, then we can write net electric current flowing through the depletion region to be equal to I hope you can understand from where this negative sign came. When the junction is unbiased, only the magnitude of diffusion current and generation current is equal, not their directions. So we have to introduce this negative sign. Now net current will be equal to let this equation be first equation. But at the end we still don't know what is the value of I naught. So our derivation is not finished yet. Now we have to mark few points which are important for our further derivation. Let this point be representing magnetic area hole concentration in the n-type region when the PN junction is forward biased, which is represented by P n naught. This point Pn is representing the value of hole concentration if it was unbiased. Similarly, this will be Np naught and this point will be Np. We have represented 4 points, but there are actually 8 points. Other points which can be defined are Pp naught, Pp, Nn naught and Nn. It is quite obvious what these parameters represent. I will not be representing them in the diagram because it will make the diagram more congested. We have a formula which is hole concentration in the p-type region is equal to hole concentration in the n-type region multiplied by exponential q into v naught divided by kt. We have already derived. Similarly, we can write pp naught is equal to Vext represents forward biased external voltage. These two equations are sometimes referred as law of junctions. If we divide these two equations, then we will get you can assume that the hole concentration Pp is approximately equal to Pp naught. Although the absolute increase of the majority carrier concentration is equal to the increase in minority carrier concentration in order to maintain space charge neutrality, but the relative change in majority carrier concentration can be assumed to vary only slightly with forward biasing compared with equilibrium values, such that it will give Pn naught equal to Pn into exponential Q into V external divided by Kt. Similarly, we can write Np naught is equal to now we will define another parameter delta Pn, which is equal to Pn naught minus Pn. It simply represents the difference between the hole concentration when the diode is forward biased and unbiased. This value here represents delta Pn. You can write delta Pn to be equal to in the expression of delta P, V is representing applied external voltage which is equal to Vext. Basically, both Vext and V are actually the same. Similarly, we can define another parameter delta Np, which can be written as now we can write the change in the hole concentration with respect to thermal equilibrium value as a function of distance xn like this. This equation we have already derived in special cases of continuity equation, where we assumed that the electric field is zero and the current is mainly due to diffusion. The topics of the first unit are very important, and this is the reason why. Because many formulas which we have derived in the first unit are directly used in topics of other units. If you can recall what I am talking about, then it is good. Otherwise, you should watch that lecture again. Similarly, we can write the derivation of the change in free electron concentration from the thermal equilibrium value as a function of x like this. The whole diffusion current at any point xn in the n-tap region can be calculated as here we have assumed that A is the cross-sectional area. This means that the whole diffusion current at every position xn is proportional to the excess hole concentration at that point. Now we will find the total current coming out of the depletion region into the n-tap region by simply putting the value of xn to be equal to 0, which actually means that we are finding the value of current at xn naught. By a similar analysis, the injection of electrons into the p-tap region leading to an electronic current at the junction which is equal to Now we are going to do the most important step of our derivation, in which the net current is equal to current due to holes at the junction in the n-tap region minus current due to free electrons at the junction in the p-tap region. You may think why there is a negative sign. The reason is that in this step we are considering the two Cartesian system. In the beginning we assumed different directions for xp and xn to be positive. But here we have to combine these two different currents. If you see for the expression for whole current, then you got positive sign, meaning that the whole current is flowing from left to right. And if you see in the electron current, then we got negative sign. But for the xp, we have taken positive side from right to left. Therefore, inclusion of negative sign means that the net current due to free electrons is actually in the direction from left to right. Therefore, the two currents are actually in the same direction. And this negative sign in the final expression will cancel the negative sign which is present in the expression of current due to free electrons. Therefore, net current will be equal to let this equation be second equation. We got these two equations which are very important. Second equation is the equation by which we can actually calculate the current with the help of parameters defined for the semiconductor. And upon comparing these two equations, you can find the value of I naught to be equal to Now we are going to see a very special case which is very important as well. We have assumed that the external voltage is forward biased, but if we apply a reverse bias voltage, then V external will be negative. Let us represent it with minus VR so that it becomes clear that the semiconductor is reverse biased. Now put the value of this external voltage in any equations. I am taking the second equation. Now, if we assume that applied reverse bias voltage is significantly greater than kTyQ, which is thermal voltage, and is equal to 26 millivolt at room temperature, then you can see that the exponential term becomes very small compared to -1. Therefore, net current will become, and we just found that this expression is actually equal to I0. Therefore, for high reverse bias voltage, net current across the depletion region is equal to minus I0, and for the same reason, I0 is given the name reverse saturation current. Therefore, I0 is actually the maximum theoretical value which can flow through the PN junction when the junction is reverse biased. This lecture is very important. Each and every step is important. It may be possible that no questions related to the derivation may come, but still, it should be clear to you that how this formula came into existence. Formulas you have to remember obviously. Many questions will be framed from it, and you should also know why I0 is called reverse saturation current.